Okay, welcome to chemistry lesson 2. All right, so I wanted to talk about how in the previous lesson I sent out the Zoom invitation out really late, and I was hoping more people would show up because I was expecting the rest of you to do a self-introduction, but no one else is here except Angela, so shout out to Angela for being the only person who shows up, okay? And doing all the activities last time. Okay. I wanted to say that if you guys had any questions, please tell me because the purpose of this lesson is for you guys to learn. And that I realized in the previous lesson, sometimes my mic wasn't clear. I think I fixed that. It shouldn't happen again. So, yeah. Previous lesson points that I didn't teach well because I did not give enough examples. So, review. Okay, I remember that I didn't teach the graphing part well about volts. So if you remember, volts stands for variables, arrows, units, labels, title, and scale. So for variables, you can see when I title the graph, I have the letter T beside temperature of water. The T is to represent temperature of water, and the lowercase t represents time. These are the variables. We need variables because sometimes when we're writing formulas, did I ever show formulas on the next page? Oh, there we go. Okay, I'll explain why we need variables on the next slide. Arrows, again, on the axes of the graph, and on the graph itself, it is continuous data. Units, so in brackets on your axes. Labels, labeling your axes. Title, and scale. So, scale, fine. Yeah. So why do we need to use variables? Here I've given a scenario where you perform a ticker-tape experiment, which is something you will do if you take physics, but that's not important right now. Wait, yeah, you will do a ticker-tape experiment in physics in Science 10. Ticker-tape is something used to record the speed of an object or the acceleration of an object, but that's not important yet. So you're performing a ticker-tape experiment of a toy car rolling down an incline. There's no manipulated variable in this experiment, blah, all right, so why do we need variables? When we're writing formulas, for example, when calculating slope, I don't know if you guys have learned this in class yet, but slope is equal to change in y over change in x. And to represent that, oh wait, we have a new participant. Give me a second.
Is everyone here?
To represent the change in y and x, we will substitute the y with the variable we have given for the y-axis and the variable we have given for the x-axis, which is t, where the slope is equal to acceleration in this graph, and the y is equal to velocity, represented by v, over time, represented by t. Okay, something else I didn't teach well in the previous class was the chemical property, physical property, etc. Here we have examples of chemical property. So something that supports combustion is a chemical property, something that reacts with water, and something that's flammable. Whereas a chemical change, as I described before, a change is like a verb. So silver tarnishes, that is a chemical change. Baking soda reacts to vinegar and iron rusts, blah, blah. All right. Physical property includes physical descriptions of an object, such as blue color, the density of an object, solubility, sour taste, etc. Physical change, examples include salt dissolves in water, water turns to steam, alcohol evaporates, where the chemical makeup or the molecule of the object itself remains the same. All right, moving on to the lesson itself and not the review. Parts of the atom. So first off, the first main part of the atom is the nucleus, which contains two major subatomic particles, which you will learn about more on the next slide. The two major subatomic particles in the center of the atom are protons, which are these things, and neutrons, these things. So if you remember here on the right, this is a Bohr model. And then this here on the left is the most up-to-date model, the quantum mechanical model of the atom. Okay, so in an atom, there are three major subatomic particles. Firstly, the protons. They're relatively large particles with a positive charge represented by +1. They're found only in the nucleus of the atom, and they weigh 1 atomic mass unit. AMU, atomic mass units, also written as AMU, it's just a weight unit. I don't know the conversions for it from kilograms, but all you need to know is that it's just a weight unit. The second major subatomic particle is the neutron. They're also a relatively large particle, about the same size as the proton, and they have no charge. And that's why they're called neutrons, as in neutral. And then protons, as in pro, like positive. They are also found in the nucleus with the protons, and they also weigh 1 atomic mass unit. Next up, we have the electrons, which are represented by E followed by a negative sign, or this is the symbol of an electron. They are a tiny particle with a -1 charge, and they're found in a cloud around the nucleus, which is the electron cloud. But if you're using the Bohr model, then they're just in levels or shells around the nucleus. They weigh approximately 0 atomic mass units. They do have a mass, but it's too tiny to measure. Or at least with the units that we will be using in Science 10, they are too tiny to measure. So atoms themselves will always have an equal number of protons and electrons so that they have a neutral charge, since protons have a +1, which is neutralized by the electrons, which have a -1 charge. Energy levels. So, energy levels is something most clearly described and shown in the Bohr diagram, which are these things. They are also known as shells. They are occupied by electrons, which are represented by the black dots on this diagram. And each energy level has a max amount of electrons it can contain. These energy levels fill in from the innermost level to the outermost level. So for example, you see here with lithium, the first energy level can only contain a max of 2 electrons. I'll explain more on this later, but once it is full, electrons in the lithium atom will start filling up their second shell. Yeah. So you can see here, fluorine has 2 electron shells. Aluminium, it has enough electrons to fill both of its first 2 shells. So it starts filling, when it has more electrons, it starts filling up its third shell. I don't think I explained that well. Any questions? Yeah, okay. So no questions.
Do you know what's going on?
You guys can unmute. I feel awkward just sitting here in silence. Okay, well, ignore this really bad meme, but our next topic is ions. Okay, back onto the periodic table. If you remember, periodic table is organized in two ways. First, we have the group number, which represents the columns, and then the period number, which is used to describe the rows. So what do these represent? The period number represents the number of shells or energy levels each electron has. Each element has. For example, here we have lithium. You can see here that it has 2 energy levels. That means you can find lithium in period 2 of the periodic table, which is here, period 2. We have fluorine, which also has 2 shells, so you can also find it in period 2. There's fluorine. And then aluminium, 3 shells, which means 3 in period number 3. And here we have aluminium, period 3. Next, group number. So group number, sometimes in the ones position of the group number. So for example, in group 13, we would use the number 3. The number in the ones position represents the number of electrons in the valence shell, which means the outermost shell of the atom. Now, using the number in the ones position to find the number of electrons in the valence shell doesn't apply to the transition metals, which are in from group 3 to group 12. We now have a new participant. Let me accept them. Hi. Give me a second, they're still joining. Okay, new member, Fairly Wang. I am going to pause my lesson to force you to introduce yourself. Fairly Wang, are you able to unmute?
Yeah.
That's cool.
I will stop my recording. Pause my recording. Wait, that's not it. There. Okay.
Hi, Fairly.
Hello.
Yeah, that's your other instructor, Tony. All right, group number. Group number represents the number of electrons in the valence shell, which means the outermost shell of the atom. So for example, we see lithium, it has 1 electron in its outermost level, which means you'll find it in group 1. And here you can see lithium in group 1 of the periodic table. Wait, can you guys? Never mind. Oopsies. Ignore that. Technological difficulties, I'm sorry. Okay. And then you see here aluminium, right? It has, I believe, 3 electrons in its outermost shell. That means you can find it in either group 3 or group 13. Aluminium. All right. It is not break, guys. As you can see, I am going to make you guys do exercises, I think. Give me a second. Oh, you can now see my whole screen. I turn off screen share and quiz them. All right. So let's have Fairly Wang unmute herself because Angela had to answer all the questions in the previous lesson. Oh wait, no, you missed the first part of the lesson, so you won't be able to answer these questions. Tony, come up with an idea on how to quiz them.
Okay, so only 2. The only 2. Hold on. Okay. Does Fairly know like a little bit what's going on? Like Fairly, do you have any idea like how chem and science 10 works, or are you completely new to this?
I have a little like knowledge about it.
Okay. Okay. So Rachel, can you just quickly steam through the lesson, like just go on each slide for like a second or two, and then after she can assess like if she has enough abilities to answer these questions or not.
Okay.
Okay.
All right. Actually, I'll ask Fairly first what she knows. Do you know things like chemical change and physical change? This kind of
Yeah.
stuff? You
Yeah.
can see my screen, right? Yeah. So let's see. So do you think I can kind of quiz you on that?
Sure.
Sure. All right. Here we go. If something is explosive, does that mean? Okay, wait. Let's say oxygen is explosive. Can you see my screen? Like this? It should say Google Jamboard on the top of the tab.
Yeah.
Yeah. Okay. Let's say oxygen is explosive. Is this a chemical change, property, or a physical change or property?
Chemical change?
Oxygen is explosive. You're close. Give it another shot.
Chemical property?
So if something is explosive, in my lesson, I actually talked about that when you describe something as a change, it's usually used like a verb. So for example, milk sours. If you want to turn this into a chemical property, you can write it as milk can sour. Actually, I should write that under chemical property. Oopsie daisies. I'll do that later. So, if you were to write, wait, how can you change this oxygen explosive phrase from a phrase of chemical property into something that represents chemical change? How do you explain this as a chemical change? There we go.
Oxygen exploded?
Yeah, that is correct. All right. Stack of papers gets stapled together. Physical change, property, or chemical change or property?
Physical change.
Yeah. And then, a potato explodes. Go.
Chemical property?
Try again.
Physical change.
You could call it physical change, actually. Yeah, that counts. And then how would you convert this into a property?
Potato explodes?
How would you convert this sentence into a property instead of a change?
Potatoes can explode.
Yeah. Okay, what is the next topic to quiz on? Because I high-key made this lesson last minute, but let's not talk about that. Oh, okay, sure. Which of the three major subatomic particles will you find in the neutron? Angela. Unmute.
Protons, neutrons. Protons, neutrons, electrons.
Those are all the three major subatomic particles. Which of them would you only find in the nucleus of the atom?
Okay. But I kind of I didn't so for that slide, I kind of didn't see it really.
Really? Okay. Here we go.
Okay.
Yeah, I can go over the lesson again. So, information about your element. Something we use, wait, what am I trying to say here? Oh, okay, atomic mass number. Okay, the atomic mass number is the weight of an element. It is represented by the letter A, capital A, and it's equal to the number of protons plus the number of neutrons. So if you remember, a proton weighs 1 atomic mass unit, and a neutron also weighs 1 atomic mass unit. By combining the number of protons and neutrons in an element, you get the total mass of that element. For example, why do I keep doing that? For hydrogen, it weighs 1 atomic mass unit. Usually, which is, you can see this number here. Usually hydrogen only just has 1 proton. For things like boron, you can see that it weighs approximately 11 atomic mass units. So that means there's a total of like either 11 protons and neutrons inside that element. Now you can rearrange the formula of A equals protons plus neutrons to find the number of protons or neutrons in an element. So for example, this number you see in the periodic table to the top left of all elements is the number of protons in that element. So carbon has 6 protons. And then if you remember, atomic mass number is represented here on the bottom, which is approximately 12. So carbon has an atomic mass number of 12 and 6 protons. By rearranging this formula, we can find the number of neutrons in carbon. So to rearrange this formula to find the number of neutrons, we'll just subtract the number of protons from the atomic mass unit. For the case of carbon, it will be 12 minus 6, which is equal to 6. So carbon has 6 protons and 6 neutrons. Moving on. Atomic number. Atomic number is the number that represents an element. So again, the number you will usually find on top of the element on a periodic table or to the top left. So again, this number up here. 1 for hydrogen, 3 for lithium. The atomic number, which is represented by capital Z, is equal to the number of protons in that element. Elements will always have the same number of protons. This will never change, but this doesn't apply to electrons. An element can have the same number of protons, but the number of electrons it can have can change, which we will explain in a later slide. Okay. Notation of an element. When you're writing down, Tony, explain this notation thingy.
Okay, so this notation is, so you see, so the atomic number of something is just like the order that it comes in on the periodic table, right? But the number is also equal to the, like 1, 2. Can you go back to the table?
Yeah.
Yeah, so it's like 1, 2, 3, right, etc. But the number also represents the mass. No, not the mass. The number. The reason why everything has a number is because the number is like the number of protons and electrons in a element. Like the amount is the number that they're given on the periodic table. So hydrogen will have 1 proton and 1 electron, and then helium will have 2 protons and 2 electrons, and that's basically why all the elements have a respective number. Okay, and then, yeah.
I was trying to get you to explain this thing, but sure, explain.
Yeah, no. And then, so that's Z, right? That's a number, right?
Z.
So then let's talk about A. So A is the atomic mass. So A is basically how much it's not, well, later you'll learn that so there's a certain amount of molecules that a scientist uses to like weigh itself. So basically that's called a mole. So the A value is just how much 1 mole, so like how many of molecules weigh in grams, right? So if you go back to the table, all right, that number is the number that is on the bottom. So under hydrogen, you can see like that 1.00, there's an 8, I think. And then helium, you can see the 4 something, right? So the reason why we have this notation is because if you take the mass and you subtract it by the number, right, you get the number of neutrons that are in the element. Because if the number of protons are the same as the element number, then that is just an easy like subtraction problem. So yeah, it's just for convenience.
Okay, so Tony actually expanded a bit too much into atomic mass. You might have heard him say something called mole. That is something you will learn in Science 20 or Chem 20. Don't think about it yet. So this thing here is what's known as nuclear notation. It's one way to represent or to write an element. Someone is talking to me. Oh, shoot. Well, I'm sorry. Okay.
Just don't worry about moles, but basically the number doesn't come out of anywhere, okay? Like scientists actually need to take like a certain amount of the element and measure it and average it out. And that number needs to be constant throughout all of the experiments.
Okay, actually something else I should mention is that you guys remember how I said that protons weigh 1 AMU and neutrons weigh 1 AMU. And these masses are equal to the sum of the protons and neutrons in that element. Except when you look on here, you'll see that these aren't perfect numbers. They have decimals, which doesn't make sense since protons and neutrons only weigh 1 AMU. That's because there are different versions of an atom. Atoms actually can change the number of neutrons they have. So if you remember before, I said that elements can never change the number of protons they have. That is the only subatomic particle that remains constant throughout all the elements. The other subatomic particles, neutrons, electrons, the number of those in each element can change. This number here is the average atomic mass unit of this element. So this includes, so boron can have from like anywhere from maybe, for example, 5 to 10 neutrons. They'll find the average of all the different versions of boron, the average mass of all the different versions of boron, and then that's what you find here. That's why there's decimals under mass. All right, back to what I was trying to teach. Nuclear notation. Basically, to write an element in nuclear notation, on the top left, you write the A, or the atomic mass of that element, which for carbon is 12. Oh yeah, just round the decimals. When you're writing the atomic mass for these things, just round it to its closest whole number.
Yeah. Yep.
So top left, you would write the atomic mass number of that element. Bottom left, atomic number, if you remember, is represented by Z. So the number of protons in that element. And then you would write the in one giant letter, the symbol of the element itself. So in this case, we have the nuclear notation of carbon, where it has a mass number of 12, an atomic number of 6, and the symbol for it is a giant C. Isotopes. So isotopes are the names given to an element with different numbers of neutrons. Again, as I said before, elements can change the number of neutrons they have. And because of this, they can have a slightly different mass. Now, each element has kind of like a chemical reaction sort of unique to it. But by changing the number of neutrons they have, it does slightly also affect their chemical reactions of that element. So how do we explain an isotope? When I tell you I have 6 carbon molecules, by default, you will assume the atomic mass of that carbon molecule is 12. But to explain an isotope, for example, if I'm talking about a carbon that weighs 14 atomic mass units, which means it has more neutrons than the normal carbon, I will call it carbon 14. If you, yeah. So another way to say the names of atoms is to say the name itself, and then followed by the atomic mass unit of the atom you're talking about. So if I say something like potassium 46, it means I have potassium that weighs 46 atomic mass units. It's written this way, where you write the name of the atom itself, followed by a dash, followed by the number or the mass of that element. When do we show atomic mass? What? Oh, I know what this is. Okay. If you see this point here I have saying you can say carbon 12, but unnecessary, implied. So again, carbon, if you look on the periodic table, has a mass of 12 AMU. You can say that you have carbon 12, but you don't need to say that because the default, it's kind of like the default mass of carbon is 12. All of the numbers you see here is kind of like the default mass, where you don't have to say their mass after the name itself, because everyone just assumes it is the default mass. Atomic molar mass. So atomic molar mass, again, the average, this stuff here, that's the atomic molar mass, represented by A, I think. Average mass of all the isotopes. So as I mentioned before, the atomic molar mass, the reason it has decimals is because it's the average mass of all the different forms of that element with the different numbers of neutrons it can have. Whoa. Ionization, this is pretty important. Ionization is the process which an atom undergoes when it loses or gains an electron. An atom with more electrons or less electrons than their normal form is called an ion. The definition of an ion, if you want to write it down, is an atom of an element with a different charge. That's actually a pretty bad definition. All right. So you can see here we have a sodium atom with all its electrons around it, and then it loses an atom, an electron, and then, wow, it's here. Okay, so if you remember, atoms will always have the same number of protons and electrons. When these numbers are unbalanced, that means they become an ion. Now to find the charge of an ion, okay, I should mention that ions have a charge. There you go. To find the charge of an ion, you take the number of protons it has subtracted by the number of electrons it has. The charge of an atom is written in superscript. So here we have sodium, which has no charge. But here, because sodium has lost an electron, it now has a charge of +1, which you will write with a positive sign on the upper right of the element. So this is one way to show or represent an ion as a Bohr diagram. Another way to show it is, this is another way to represent an ion, where we have an oxide ion with a charge of -2. Ah. So let's see, wait, sodium has 11 protons. Okay, so expanding on my example here, since sodium has 11 protons, this sodium atom will have 11 electrons. And then let's say we don't know the charge of this sodium ion. We know that sodium itself has 11 protons. And if we count the number of electrons on here, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, we'll know that there's 10 electrons. And remember, to find the charge, you take the number of protons of that element, and then you subtract it with the number of electrons in the ion. So in this case, it's 11 minus 10. So the charge of this ion is +1. However, we can also have ions with a negative charge, which you can see here with the oxide ion. Again, oxygen has, let me count actually, 1, 2, 3, 4, 5, 6, 7, 8 protons, and therefore its atom will have 8 electrons. But its ion here has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 electrons, there you go. And to find the charge of this ion, we'll take the number of protons, 8, minus the number of electrons in that ion, which is 10, which is equal to -2. Therefore, its charge is -2. Types of ions. So an ion with a positive charge is called a cation. Usually metals are cations. Okay. Yeah, usually metals, when they turn into ions, they will have a positive charge. And then an ion with negative charge is called an anion. Anion. There we go. Usually nonmetals will form anions. There's another type of ion, which is a polyatomic ion, which is an ion with 2 or more atoms. So an example of this would be NH4, which is an ion. You don't need to know this yet. You might learn this later, but I don't know. So again, a cation. Here we have sodium, which is a cation because it is a positive charge. And then this oxide ion is an anion because of its negative charge. Zainab, I'm gonna call you up. Okay, do you know or remember why? Because I think I taught this in the previous lesson. Elements lose or gain electrons.
Because they form ions, anionic bonds.
Oh, okay, ionic bonds. Yo, that means you learned this in class already. You learned.
No, like this semester I have science, so we just started. Like we started, so I sort of know.
So the reason atoms lose or gain electrons, they actually have a reason for this. I don't know why atoms can lose or gain neutrons, but you need to know why they gain or lose electrons. Basically, all atoms want a full valence shell. And if you remember, each valence shell has a max number of electrons it can have. So to get this full valence shell, some atoms, like sodium, will decide to lose an electron to lose the shell so that they have this full shell instead of a shell with 1 electron. Or in the sake purpose for oxygen, they will gain electrons to get a full shell. Depending on whatever is easiest. If it's easier for them to lose an electron to gain a full shell, they'll do that. If it's easier for that atom to gain electrons to get a full shell, that's what happens. I don't think that's a great explanation, but I hope it kind of makes sense. Okay, for atoms, each atom, they for metals and non-metals, they will only have one kind of charge. The sodium will only form an ion with a charge of +1. It will never make a charge of like -1 or +2. Oxygen will always have, when it forms an ion, only form an ion with a charge of -2 and will never become a positive charge. Unless we are talking about the transition metals, because again, they are special and we do not like them because they're really annoying since they're so special. Moving on, valence electrons. Valence electrons means the number of electrons in the valence shell, also known as the outermost shell or energy level of an atom. Oh shoot, I had a point here where I talked about why atoms lose or gain electrons. Well, I already explained that. Oh, there we go. What happens when an ion is formed? What happens when an atom gains or loses an electron? Yes, I can talk about how to make bombs. Okay, when an atom loses an electron, when it gains an electron, it releases energy. If we remember, alkali metals, which is the elements in group 1 of the periodic table, I mentioned that in the previous lesson that they're very reactive. So basically it means when they lose, they lose electrons. Right, Tony? They lose electrons, or do they gain electrons?
The first one, right?
Yeah.
They lose electrons, but the energy that it's like the amount of work, like quotation marks work, it takes to lose and gain an electron is about the same. So like hydrogen can gain or lose,
Okay, well,
but all the other ones lose.
Yeah. Basically, the alkali metals, they lose an electron. When they lose this electron, because of their high reactivity, it releases a lot of energy. Now, we can use this to our advantage, use this release energy to our advantage. So for example, one of the highly reactive things you see here is hydrogen. And I think you guys might have heard of hydrogen bombs. Very effective bombs. Bad for humanity, but they're very effective. Yeah. What happened here? Okay. Oopsies, wrong slide. There we go. Oh yeah, all right, the number. So I talked about how each energy level has a max number of electrons it can contain. To know the max number of electrons that energy level can have, you count the number of atoms in that period on the periodic table. So, for example, here, okay, what am I trying to show here? There we go. The first energy level can only have a max of 2 electrons. You see here in period 1, there are only 2 elements in period 1. Looking in period 2, there are only 1, 2, 3, 4, 5, 6, 7, 8. 8, there we go, 8 elements. So in period 2, the energy shell 2, it can only contain of a maximum 8 electrons. And then shell 3, for sodium, its third shell isn't full, but the max number of electrons shell 3 can have is also 8. And if you keep going, fourth shell can contain about 18, fifth shell 18. You don't need to remember how many electrons each shell can have past group. Okay, you need to remember the max number of electrons a shell can have for shell 1, 2, and 3. You don't need to remember that shell 4 can only have a maximum of 18 electrons and 5 a max of 18. But memorize that first shell can only have 2 electrons at max, Second, 8 electrons at max. And third, 8 electrons at max. Octa Rule. You don't need to remember the name of this rule, but just know what the rule itself talks about. Octa Rule means rule of 8. I don't know why it's called that, but the Octa Rule just means atoms like to bond to create a full valence shell. So most of you guys have probably heard of things called molecules. Molecules are when two elements or two atoms bond together. So, what am I trying to say here? Atoms bond. There we go. The reason atoms bond, if you remember, atoms want to have a full valence shell, right? All right. But to gain and lose electrons, they can't just have free floating electrons in the air. The only way they can gain electrons is by taking it from another atom. And if you remember, some atoms want to lose electrons and some atoms want to gain electrons. If these two atoms, the one that wants to gain, the one that wants to lose, bond together, they create a molecule where both of them are happy because they got what they wanted. There we go. They got their full valence shell. This kind of compound or molecule is called a molecular compound. Wow. Oopsies. Okay, so what will an ion, to have an idea of what the ion of an atom will look like, atoms will try to attain the electron configuration of their nearest noble gas. So all noble gases, if you remember from the previous lesson, they're very stable. They won't form chemical reactions because they won't gain or lose electrons. Actually, I should explain that all chemical reactions are caused by gaining or losing electrons. There you go. Attain electron configuration. So to know, back to what I was trying to say, to know what an oxygen atom will look like as an ion, look at the noble gas it is closest to on the periodic table. So here we have oxygen. The closest noble gas it is to is neon. And neon's electron configuration looks like this. So oxygen, to look like neon, to have a full valence shell, will turn into, this. What you can see, the electron configuration here, so the electrons in each cell is the same as noble gas of neon. Compounds, our next topic, our last topic for the day. Okay, first off, molecular compound. They have a covalent bond. So let's see, they have full valence shell, okay. Atoms in a molecular compound will have a full valence shell by sharing their electrons. So remember, one atom in a molecular compound will gain electrons and the other atom will lose the electrons. Wait, stop. Don't listen to what I just said. I got something completely wrong. Tony, I'm calling you up again. Is molecular compound the one with the metal and non-metal, or is that the ionic compound?
That's the ionic.
That's the ionic.
It's the ionic, with the metal and non-metal?
The metal and the non-metal is ionic.
Okay, guys, I completely screwed a topic up. It's all good. Molecular compound is when two non-metals bond together. So if you remember here, I said when two molecules bond together, one gains and one loses. That's not called a molecular compound. A compound where one gains and one loses is called an ionic compound, which I will explain in the next lesson. But we are talking about a molecular compound. This happens when two nonmetals join together. In this case, they don't lose or gain electrons, but they just share electrons. The process, the name of like sharing electrons is called a covalent bond, where they cooperate to have the number of electrons they want. Molecular compounds will always only contain two nonmetals. You'll never find a molecular compound that has a metal and a nonmetal, or anything that's not a nonmetal. Molecular compounds also don't conduct well. They can be either solid, liquid, or gas at room temperature. They also won't form precipitate. So when molecular compounds have a chemical reaction, they won't form precipitate or solids. Chemical reactions that create ionic compounds, which again you will learn later, they will form precipitate or solids. Okay, as I said on here, y'all get to sound cool now. Nomenclature means naming process, the naming process of molecular compounds. So if you remember, I didn't show you an example of a molecule. An example of a molecule is when two hydrogens and sulfur bond together. I need to give a better example. Okay, if you remember, yeah, a molecule, two atoms bonded together, right? Here we have an example of a molecule, which you can write by H and S, which is a hydrogen and sulfur molecule. What is the official name for this molecule? So to name a molecule, why did I write elements? To name a molecule, first you take the names of it and write it in all lowercase. So in this case, for this molecule, the names of it are, the elements in it are hydrogen and sulfur. You change the ending of the second atoms to end in IDE or IDE. So instead of hydrogen sulfur, you write it as hydrogen sulfide. And then you use prefixes to indicate how many of that atom there are in that molecule. These are the prefixes, and you will have to memorize them. So in this case, since we have two hydrogens and the prefix is di, we will change the word hydrogen into dihydrogen. And then since there's only one sulfide, we will change it to monosulfide. So this compound, H2S, is called dihydrogen monosulfide. So there is an exception to this prefix thing, where if the first atom, so the atom on the leftmost of that molecule, there's only one of that first atom. For example, in CO2, you don't need to say mono. You don't need to say, oh, there's monocarbon. There's only one carbon. Don't worry about it. Why? Because we're lazy. And then when the first atom when there's only one version of the first atom in the element, we just don't say mono. You assume there's one. So if you guys remember, most of you probably know carbon dioxide. We don't give it the prefix of mono. We don't call it monocarbon dioxide, but just carbon dioxide. Now you know why CO2 is called carbon dioxide. That's pretty cool. I mean, I thought it was cool when I learned that. All right, fun story time. This is a story given by my junior high science teacher about a science experiment, I think, performed at the University of Calgary. So, do any of you know maybe how hydrogen monoxide can be written as, oh my God, what's it called? Its chemical formula. I need to explain this. A chemical formula. This is the chemical formula of a molecule, where you show it with its symbols. This is the notation, nomenclature. Oh, what am I trying to say? This nomenclature, okay? Nomenclature of a molecule, this is called its IUPAC name. So let's say we have dihydrogen monosulfide. The IUPAC name is dihydrogen monosulfide. But the chemical formula, where if you were to write it with its symbols, then it's written as H2S. Now, using this IUPAC name, dihydrogen monoxide, can you guys figure out what its chemical formula is? As a hint, it is a very common chemical. You drink it a lot. Yeah, H2O. Okay. Let's call it fairly. Fairly, what's another name for H2O? What do we usually call H2O? Oh boy, I have to click on the chat again. Yeah, all right. Oopsies. So, basically, UC experiment. I don't know what this experiment was supposed to be on. I think it was a social experiment or something weird like that. So my teacher, Miss Anko, her friends made this experiment where they went around City Hall in Calgary and they would interview people and they'd tell people that they were making a petition to get rid of dihydrogen monoxide from Calgary's water systems. They told the people that the hydrogen monoxide causes thousands, many deaths every year. Basically, it's really harmful, right? And then so many people signed that petition to get rid of dihydrogen monoxide from Calgary's water systems. So very few people got the joke when they were doing this experiment. But yeah, I did not explain this story very funnily.
That's funny. But basically she said things like, when it's very hot, it can burn you, or it can get up in your lungs and create a lot of steam. And she said you can choke on it. It can be a choking hazard. And she basically said every quote-unquote hazard that water gives you, but she just acted like it was so dangerous. Yeah. But I should add that you shouldn't name water like H2O or HOH, like dihydrogen monoxide, because there are some molecular compounds that have like common names, and those are like technically the proper names. So we should just go by them. And so water, H2O, is just water. So you don't need this complicated chemical formula.
Okay, what Tony is saying is that water can be called dihydrogen monoxide, but nobody says that. So don't bother.
No, like the official name is not dihydrogen monoxide, so we should not call it that.
Don't care. If you see H2O, just say water. You can technically,
because that's its real name.
You can call it dihydrogen monoxide, but don't.
No, you can't, bro.
Yes, you can.
Okay, so on a test, right? This is true, okay? But on a chem test, you're always gonna get a question where there's gonna be a compound, right? And it has a common name, but its like chemical name is also gonna be one of the answers, and they're always gonna want you to pick the chemical name, but you're supposed to pick the common name. So at DEEF, the one they use every year, and the teacher actually said they use this every year, right? It's methane, CH4, right? That is the proper name for methane, for 4CH4, methane. So if you ever see like name this, you put methane. You don't put carbon tetrahydride. Like if someone has a common name, that's its quote unquote real name.
Okay. So what another way to phrase what Tony is saying is, in tests in school, you'll see them write compounds like this, for example, H6S4 or H2O, and they're going to ask you, what is the IUPAC name or the molecular nomenclature of this compound? For H2O, do not write dihydrogen monoxide, write water. Okay, there's like, what do you guys want to say? Stop. Yeah. All right. So I'm gonna show this here. All right, you can see the prefixes, right, guys? Yes, you can. Okay. Let us give you a compound. Let's say I have H6S4. Using the molecular nomenclature process, how would you name this compound? And then once you get the answer, just type it in chat.
Rachel, are you good? What's happening?
Oh wait, did you guys not hear? Okay, maybe I didn't talk it loud enough. Using molecular nomenclature, write the name of this compound, and once you figure it out, write it in chat. Type it into the chat.
Wait, actually, don't type it in the chat. Everyone do it, and then we're going to call on one of you, and you're going to tell us through your mic.
How would you know when they're done, though?
You get 30 seconds.
No, that's not enough time, Tony. Is it enough time? Wait, Tony, can you guys see the chat when I open it on my screen? Tony.
No, they can't see the chat, but
On my screen.
okay. So we'll give you like 10 more seconds because it's not the hardest thing in the world because hydrogen, sulfur, like they're right there. Okay.
Fine.
Okay.
I will go through the process. Actually, I'll just go through the process with them.
Okay, wait. Let's call on someone first. Okay. How about? All right. How about fairly? What do you think this molecular compound is named?
Hexahydrogen tetrasulfide.
Yeah.
All right, that's good. Very good.
That's actually good. Okay, I don't know. I thought this was hard. Okay, I didn't expect them to get it this quickly. I'm actually proud. I'm actually so happy. I thought I taught it pretty badly. Yay. Okay, let's call up someone else next. I get out of subscript. Oh shoot, the lesson's ending. Oh my god, it's almost 5 o'clock.
Okay, just finish it off with one more. Just write something. Write something.
Sure. Let's see. This works. Sure. I'll give you guys like a minute.
Is 6 your favorite number?
No, I don't know. It just came up as a default.
Hey, do like, you know what? It's fine. But yeah.
You have something against 6?
Since it's a repetitive question, like the students will get experience with other numbers.
Here, you guys should be able to change this pretty fast. I'm gonna do a change. Tony, give me a number. Oh, actually, you want no number. There we go. Just CH10.
C3H8.
C3H8. Why? Fine. C3H8 because Tony said so, guys. I'll give you all like 30 seconds.
Okay, I feel like that's enough time.
Okay, sure. Go. Okay, yeah, you call up someone.
All right, Zainab, do you want to answer this question?
Yeah.
Yeah. So what do you think the name of this molecular compound is?
I think it's tricarbon decahydride.
The first step, remember.
Well, we changed the number a lot, but
Yeah, sorry.
Oh, okay, octahydride.
Yeah. Wait,
Yeah,
Zainab,
okay.
did you learn this in school already, or did you actually learn it from me teaching?
Yeah, I learned it from you. We did the ionic nomenclature, but not the molecular one. yet.
Okay, I'm glad I actually taught it decently. This makes me so happy. You don't understand, guys. And
Well,
I'm
like
so
here's
happy.
the.
What?
I was gonna say here's the catch, but you can have your moment.
Oh, go away, Tony. Okay, no, I'm a great teacher, and these are great students who pick up things quickly, and I love them. Now you can
Yeah.
talk about your catch.
All right, my catch is basically like, you know how I was talking about how like some things have common names.
You're gonna
Like-
throw shade at me for my dihydrogen monoxide. Cool.
But
Okay,
see-
before you guys hear
no.
Tony's shade, you can leave the class now. All right? You guys don't get to hear
No,
Tony
it's
throwing
actually
shade
an
at
important
me.
part. But C3H8 is the chemical formula of propane.
Well, go away, Tony.
So like next class, like we
We will
need
teach
to like
common names.
teach you guys some common names.
Tony will teach
So-
more on
But,
molecular compounds.
Yeah.
So yeah, thank you for attending this class. Y'all were great students.